Hello, I'm Sebastian. Welcome to 9 Trees podcast. Today, I will summarize and review the book. Introduction to Quantum Mechanics by David J. Griffiths is a widely used undergraduate text that guides students from the conceptual shock of quantum behavior to the practical tools needed to solve standard problems. Known for its clear explanations and carefully chosen examples, the book builds intuition while steadily developing the mathematical formalism. It introduces the wave function and its probabilistic meaning, then moves through central model systems such as the infinite well, the harmonic oscillator, and barrier tunneling, showing how quantization emerges from boundary conditions and symmetry. Along the way, Griffiths emphasizes how to think like a physicist, translate physical assumptions into equations, apply approximation methods when exact solutions are unavailable, and interpret results in terms of measurements. The writing is approachable without being simplistic, making it suitable for students encountering quantum theory for the first time, as well as for self-learners who want a structured path into the subject. I will give you key takeaways from this book. Firstly, wave functions, probability, and the meaning of measurement. A central theme of the book is the shift from deterministic trajectories to probabilistic predictions. The wave function becomes the primary object. It encodes everything that can be known about a system, but only in the form of probabilities for measurement outcomes. The text develops how probability density is obtained from the wave function, why normalization is required, and how expectation values summarize predicted averages for repeated measurements. It also clarifies the role of operators as the mathematical representation of measurable quantities, tying them to eigenvalues and eigenfunctions as the allowed results and the states that produce them with certainty. This topic naturally introduces uncertainty relations as a quantitative limit on simultaneous knowledge of conjugate variables, framing uncertainty as a feature of the theory rather than an experimental flaw. Griffiths typically reinforces these ideas with basic, one-dimensional examples and with interpretive discussion about what a measurement does to a state. By focusing on calculation and interpretation together, the book helps readers avoid treating quantum rules as disconnected formulas and instead see them as a coherent framework for predicting outcomes in the laboratory. Secondly, the Schrödinger equation as a problem-solving engine. The book presents the time-dependent and time-independent Schrödinger equations as the core dynamical law, then shows how most introductory quantum mechanics reduces to solving boundary value problems. Readers learn how potentials define the physical situation and how boundary conditions select which mathematical solutions correspond to realizable states. Standard model systems receive careful attention: the infinite square well, finite wells, step potentials, and barriers. These examples demonstrate quantization, reflection and transmission, and the emergence of discrete and continuous spectra. A crucial highlight is tunneling, where the mathematics predicts non-zero transmission through classically forbidden regions, leading to phenomena such as barrier penetration and resonant behavior in multi-region structures. The text also emphasizes stationary states and energy eigenfunctions, explaining why energy measurements in such states are stable in time, while superpositions evolve with relative phases. Through these problems, the reader practices separating variables, matching solutions across boundaries, and interpreting what the wave function implies about localization and momentum content. The result is a toolkit for turning qualitative physics questions into solvable equations, with solutions that can be checked for physical plausibility using normalization, continuity, and limiting cases. Thirdly, quantum states, observables, and the structure of operators. Beyond solving differential equations, Griffiths developed the abstract structure behind quantum calculations. Observables are represented by linear operators acting on states, and the book explains why Hermitian operators are tied to real measurement outcomes. Commutators become a compact way to express compatibility of measurements and to derive uncertainty relations, making algebraic reasoning as important as calculus. The topic also includes how to expand an arbitrary state in an eigenbasis, turning complicated questions into linear algebra problems about coefficients and probabilities. This perspective helps students understand why eigenfunctions form a natural language for prediction. The probability of obtaining a particular outcome is linked to how strongly the state aligns with the corresponding eigenstate. The text highlights how degeneracy and symmetry influence eigenstates and how to interpret projection onto subspaces when outcomes share the same eigenvalue. Time evolution is framed in terms of how states change under the Hamiltonian operator, connecting the differential equation form of Schrödinger evolution to a broader operator viewpoint. By developing operator properties alongside concrete examples, the book prepares readers for more advanced formulations while keeping the focus on practical computations such as expectation values, variances, and the consequences of non-commuting observables. Fourthly, angular momentum and spin as quantum signatures of symmetry. A major conceptual step is moving from one-dimensional motion to systems with rotational symmetry. Griffiths introduces angular momentum in quantum mechanics as an operator with quantized magnitude and discrete components, showing that classical vector intuition must be refined. The algebra of angular momentum operators provides an elegant route to quantization rules and selection properties without always relying on differential equations. This chapter area typically leads to ladder operators, eigenvalue relations, and the idea that symmetry constraints can determine allowed states. Spin is then introduced as intrinsic angular momentum, a purely quantum degree of freedom with no classical analog but with direct experimental consequences. Spin half-systems provide a compact setting to learn two-state vectors, Pauli matrices, and measurement along different axes, making the probabilistic postulates concrete and testable. The combination of orbital angular momentum and spin also sets the stage for understanding multi-component wave functions and how internal degrees of freedom couple to external motion in the presence of magnetic fields. Even at an introductory level, this topic demonstrates the power of operator methods and symmetry reasoning. It also connects the formalism to real phenomena such as quantized magnetic moments, Stern-Gerlach-style measurements, and the discrete structure behind atomic and molecular spectra. Lastly, approximation methods for realistic quantum systems. Because only a handful of potentials yield exact closed-form solutions, the book emphasizes approximation as a practical necessity rather than an afterthought. Time-independent perturbation theory is a key method. Start from a solvable Hamiltonian, add a small correction, and compute systematic changes to energies and states. This approach explains fine shifts in energy levels and provides insight into how sensitive quantum systems are to weak influences. Degenerate perturbation theory addresses cases where multiple states share the same energy, showing how small interactions can mix states and split levels in ways that depend on symmetry. Variational methods provide another powerful idea. Choose a trial wave function with adjustable parameters and optimize it to estimate the ground state energy, producing accurate results even when the detailed solution is unknown. The book also commonly introduces the WKB, or semi-classical approximation, linking quantum behavior to classical action while capturing tunneling and quantization in slowly varying potentials. These techniques teach transferable skills, identifying small parameters, estimating errors, and interpreting approximate answers physically. Together, the approximation toolkit equips readers to move beyond toy models and toward the kinds of calculations used in atomic physics, condensed matter, and modern quantum technologies. In conclusion, this book is best suited for undergraduate physics majors, engineering students taking a quantum course, and motivated self-learners who are comfortable with calculus and basic differential equations. Readers who want both conceptual clarity and the ability to compute concrete results will benefit most, because Griffiths consistently connects interpretation to worked problem styles that mirror real coursework. Studying it can improve a reader's life in a practical sense by strengthening analytical thinking, modeling skills, and mathematical fluency, all of which transfer to advanced study and to technical careers. It also builds a durable intuition for probabilistic reasoning and for how measurement affects predictions, an intellectual shift that influences how one approaches uncertainty in any complex system. Compared with many quantum texts that are either highly abstract or overly formal early on, this book is often valued for its balance. It introduces the operator viewpoint and symmetry ideas without losing beginners in abstraction, and it provides enough standard systems and approximation methods to create genuine. For buyers comparing options, it is a strong value because it supports both classroom success and long-term reference use, with a style that invites revisiting topics as skills mature. If you would like to support David J. Griffiths, you can buy the book through the Amazon link I've provided in the podcast description. After reading the book, please let me know what you think and share your thoughts. See you around.